All right. Welcome. It's good to see you all. It has been a wild, wild week here in Oregon. The road is still closed to our house, by the way. It's officially closed. But we just go around the sign anyway because we have to get home. But yeah, there's still trees down everywhere, and it was just madness for a while. So I'm glad we're up and running and super excited. I want to first just take us all back to the bigger picture and review the overall curriculum sequence so we can orient ourselves to where we are overall and where we are at right now. So let me go ahead and share my screen and pull that up. All right. So this is the basic sequence. Basics of technology and computers, programming fundamentals, how to think like a developer, how software is made. That's where we're at right now, okay? We don't have too much longer in that area. Really, there's a bit more on how to think like a developer and go over how software is made, and we'll be done with that portion. We'll have a brief module on using a code editor, some of the basics of it. Really, with a code editor, you kind of learn by doing. And then we're going to look at the fundamentals of web development with HTML, CSS, and then a rather longer section on the core elements of the JavaScript language. While we're learning JavaScript, we're going to look at debugging strategies. So each time we're learning new things, we'll also practice how to step through your code and analyze what's going on with live code execution. After we've covered some fundamentals, we're going to specialize and look at how we use JavaScript in the web, how we use it down on the server. Then we're going to switch gears entirely and go to a whole different realm, relational databases, and then non-relational, these two types of databases. And at that point, we're going to have a brief module on project management in IT, like what are the basic strategies that are in use, just so you can be oriented, because we're then going to do a live project all together. We're going to build something for real live software. And then we'll switch to the job search process and how to get hired. So that's the overall sequence. I just want to revisit that with you. Anybody have any questions on that sequence? Okay, cool. All right. So now let's dive into some specifics. I want to talk a little bit about how it is that inside these mechanical computers, we represent these binary digits. The idea of two different states being represented mechanically and electrically has been around for a while. Can anyone tell me what Morse code is in general?
Like a series of beeps that represent letters or words or something.
Yeah.
A succession of short and long signals and each combination represents a letter.
Good. Yeah, absolutely. Has anybody ever actually heard Morse code happening?
The SOS one, that's it.
Yeah, in movies it happens all the time. I want to pull some of this up because it has a great parallel to what we do in computers. Wow, that guy's way too good. Could you guys hear that when it played? You guys hear any Morse code noise?
No.
Okay. All right.
No.
Just a moment. Probably just going to find this and send it to you. I want you to hear this. All right. So here's a typical example. Actually, we can just look at it right here. Okay. This 3 short bursts of sound pattern is an S. 3 long is an O. And if we actually do Morse code, right here, here's a nice image of it. It shows you the patterns. Now, I don't know about you, but that sure looks like binary patterns to me. I mean, yeah, it's not a number system, but there's only two states, two conditions, two symbols. They're auditory symbols, but there are two symbols. So this kind of a system, as soon as we had electronics and we're able to like send electric signals over a distance, someone devised this. It really didn't take very long at all. Samuel Morse came up with this. And it really is, in effect, a binary pattern of sorts. So we already figured out that we can use the presence of electricity and how long you keep the electricity present to represent two different digits. Because that's all you do to make these sounds is you hold a button down for a short period or a long period. This would be long, short, short, short for B right here. So that's where it started. And we're talking about like what, the 1870s or something like that. It's been a long time. I forget how long Morse code's been around, and probably Wikipedia here will tell us. Development in history, what do we got? Samuel Morse. Wow, 1844. That was on paper tape. But it's the same concept. So that's very early on. And obviously we weren't thinking about digital computers at the time, but we were already discovering that we can we can take an electronic signal, and use it as it travels to represent information on it. And we're going to come back to that. Okay. But when we first started making computers and we wanted to represent ones and zeros, we used something different. Has anybody ever heard of a vacuum tube?
Is it the thing you talked about like a couple of weeks ago to keep the signal constant, the electricity constant?
Oh, that's really, really good. Oddly enough, you're right, but it's not the specific use for vacuum tube that I'm looking at. That's actually spot on. Let me switch over to the iPad. Give me a moment. And I'm back. Okay, here's the central problem we're trying to achieve is we're trying to make some sort of device that we can control when it does or doesn't pass electricity through it. That's the central thing. Now we have these all over our houses. They're called light switches. We can walk up and flip a light switch and we are thereby controlling via mechanical action whether or not electricity flows. But for computers, we needed a system that wasn't mechanical because that's not very practical. So let me show you what we did. I'm going to stop sharing here for a moment. Actually, I'm not. I'm going to keep this up here. Okay. Here we go. All right, so here's the central problem. And by the way, this has been, I won't say a problem, just a challenge all the way through the history of computers. And so it's kind of important that you understand it. Here's what we have is we have an electricity source. I'm just going to represent it as a battery. Okay, where we have a positive and a negative. And electricity can come out of it. Now, eventually, it has to return back to the other side, but that's just electricity. We're not going to get into a bunch of theory about electricity. Now, what we want is some way where there's a device right here that answers the question, can electricity go all the way through? Or does it get stopped? And there's a lot of ways you can control that. One way is this. Where's my colors? Okay. You can have literally, just like they do with Morse code, a physical switch. It might even have a little teeny like part at the top that you can push it downward. And I'm going to make the color for pushing it be slightly different. There's the motion, downward motion. And when it gets depressed all the way downward, it is now making contact and electricity flows. And then you let go. Maybe there's even a little spring and it pops back up this way. That's mechanical. That's not very practical for computers. But what they devised later was this really cool thing called a vacuum tube. Now, there's a lot of theory here that we can get into and get very, very deep. And I'm not going to get into a bunch of electronic theory. It's not going to help us at all to do so. Just going to say this. That's not what I wanted. There we go. Okay. So we still have the situation where there's this empty spot. We want to control whether or not electricity gets through. So we're going to build a funky little device where the electricity comes in the bottom of the device. The device actually has a vacuum in it. We'll get into why in a moment. But we have a little plate down here and a little plate at the top. And the electricity can come out of the top and go into here. So if we can make it so that electricity can move through this area right here, now we have a winner. How do you do that? Now, remember, we don't want a mechanical operation. We don't want somebody to have to come and push a button to make this happen. We want to control it electronically. So for this system and any other system we're going to see after this for a computer, you have to have a second element. You have to have another signal. Now, when I say signal, I just mean electricity that can come in. And when it comes in, then electricity can flow. This signal is called various things, but most commonly it's called a gate signal because it opens the gate so that stuff can get through. That stuff being electricity. Now, again, there's a lot of theory behind how it is that a vacuum tube works. We're not going to get into that. For our purposes, it's enough to know that on a totally separate electrical circuit, if we send a signal in, as long as that signal is there, then electricity will flow. Let me go and switch this over to red. There's some highlight. Electricity, oh, highlighter. Electricity will flow all the way through. That's what we want. And then the moment that green, this gate signal goes away, this goes away right there. And electricity stops. So that gate signal is everything. This gate signal, the best way to think of this is the intelligence. This is the logic. This is the human decisions that are saying, do I have a 1 or do I have a 0? Do I have yes or no? Do I have true or false? That's what this gate signal represents. Now, in our earlier kind of like discussions about binary and representing information, we kind of were saying, well, it's the flow or absence of flow of electricity that represents the 1 or the 0. And that's true in very broad terms. What's super important is to realize that you're not even going to get that control of the flow without this gate signal coming in. And that means it's the actual logic. It's the decision maker. This electricity, let's go back to red, that can come in and travel, it is the effect of this gate signal. The gate signal is cause. Any questions about what I've drawn here so far? Well, let's get into why we don't currently use these. It's one of the biggest reasons. We've said they're vacuum tubes, and there really was a vacuum inside this tube, and these tubes were made of glass. Any idea why there was a vacuum inside there?
I have no idea.
Here's why. Now, this is some very basic chemistry and physical universe stuff, and anybody who's highly trained in science will reach through the computer and slap me. And yet it's true. You could say that there's kind of an equation which says the presence of oxygen plus the presence of heat equals degradation. In general, if things get hot and there's oxygen around, they'll do what's called oxidizing. Oxidize. It's degradation. It starts to break down physical material. Well, what do we have inside this glass tube without a vacuum? We have oxygen. And we have electricity flowing, which means heat. So the metal parts, because everything in here is metal, start to break down and degrade very, very rapidly. So what they discovered is if you take away the oxygen, then those parts don't degrade as rapidly. This is why for light bulbs, there's no air in there. Did everybody know that there's no air inside a light bulb?
I did, but only because I learned that a long time ago.
Mm-hmm. That's why.
Guess that's why they bust.
Yep. This is exactly why. So even with the vacuum in there, these things would break apart. They would break down really quickly. They didn't last a long time, and they were expensive to make. So a practical computer wasn't possible, or rather they were, but they were very, very limited in capability. Because as soon as one of these breaks down, you have no control over your 0 and 1 anymore. And you have to go and find the one that isn't working and replace it. So you can only have a computer run without any defects in its operation for a relatively short period of time, sometimes a matter of a day or 2 or 3. And then you have to go replace vacuum tubes. So it wasn't very practical. So what's the next thing they did? Well, they had the same situation. They had the problem of, here's the electricity, it travels, it needs to come back, here's a negative. And there's this space right in here, but it wasn't practical to keep using vacuum tubes. So they came up with what's called the transistor. Now, even though it ends up using an almost completely different medium than this vacuum tube, almost unimaginably different, it operates on the exact same principles. And that is that we need a gate signal to come into whatever this device is. And that gate will control whether or not electricity goes through. It's a pretty simple concept. There's nothing magical or fancy here. This gate signal, therefore, still is the 0 or 1. It's the true or false. It's the yes or no. But this transistor is really unique in that it, one, has no moving parts, and it's very long lasting. Now, a tiny bit of how it works. You have a hunk of metal. You have electricity coming in one side. You have a wire coming off the other side. This would be input and this would be output. It's the best way to think of this. This metal is silicon. It's kind of weird. Silicon's a metal. It's kind of like a mineral. It's an odd sort of funky material. One of the coolest things about silicon, though, is that it does not pass. Let me do this in red. It won't let electricity go through it. But if you take silicon and you put a tiny amount of certain other metals in it, now it changes. Let's cover 2 words. Why are you doing that? Conductor and insulator. Can anybody tell me what they think those 2 words mean?
The conductor will let the electricity go through and the insulator won't.
Yes. Yes and no for electricity. Now, again, there's a lot of theory we could go into behind here. It's really not important to do so. Big thing is conductors let electricity go through. What are some conductors that you guys can think of? What can electricity pass through?
Water.
Water, absolutely. Dangerously so. What else?
Metal.
Yep, almost all metals.
Air.
It can pass through air. It's really hard to make it do so, but it can do so. If you have space here where there's metal and another space, sorry, you have a piece of metal, another piece of metal, and if there's air in between them, they call that an air gap. The way to get electricity to flow is you have to have an extremely big voltage over here, really, really high, and then it'll jump across the air. That was a really good one. Okay, good. So that's conductor and insulator. Why do I care about that? Because check this out. I just think this is magical. If we make this really small. See if I can get rid of that blue. Nope, not what I wanted to do. All right, if we take this blue, and I was talking about this extra metal. Let's say that's not here. Let's say it's all silicon. It is not a conductor. It won't let electricity through. But if we add in this tiny amount of other metal, there's a few of them. Gallium is one. We need to get into what all the metals are. If you add that in, all of a sudden, this silicon, which has been changed a little bit, becomes something very special, which is a semiconductor. Now, we've all heard the word for many years. If you're anywhere related to the technology industry, semiconductor. This is what it factually means. You've changed this metal so that it can either be an insulator or a conductor. It can switch back and forth. Now, I don't know about you, but that is pretty amazing. And I won't get into the whole discovery and how they figured it out, except to say that the folks at Bell Labs did it. Does anybody know who Bell was? Who the human being Bell was?
Telephone guy.
Yeah, exactly. Alexander Graham Bell invented the telephone. Bell, telephone and telegraph, became American Telephone and Telegraph. These were they were the communications company in America until they got broken up. Bell Labs was the research and development folks. They had tons of money and a real strong interest in advancing digital computers. And they figured out how to make these things. And it's a wonderful story and it's really cool. All we care about is all you have to do is add in a little teeny bit of some funky little metal, and suddenly your silicon becomes a semiconductor. And I said that it can switch back and forth. How do you do that? Any ideas? Same way we did before here with a vacuum tube. If we apply a little bit of electricity to a very specific spot, it'll let it work. And I kind of described it here. I said there's a gate signal that can come in and it'll make it so electricity can go through. More precisely, the switch back and forth is produced by heat. If we warm up this metal, then it switches from being an insulator to a conductor. So what do? We have a little teeny bit of electricity that can go in and out. This is the gate. It's a very, very, very small amount of electricity. And if we put that electricity in there, it warms up a tiny bit and suddenly we have a conductor. And if we stop that electricity, it cools down and suddenly we have an insulator. and it can change state very, very quickly, and it lasts a long time. And that's all there is. The transistor symbol usually looks like this. You have a gate that comes into the bottom. You have positive coming in here and negative going here. And the gate is what controls it. That's a mistake right there. Now, again, we don't need to go deeper than that. It's not important. What you need to know as engineers, as software folks, is that as soon as this came along, now we were in business. Because one, this is a delta. This symbol is a Greek delta. I'll use this a lot. It means change. We can change between on and off very fast, very quickly. And we need that for computers. And once we solved it with no moving parts, and it was durable, now all we had to do was just keep making it faster and faster and more durable and smaller. And we got where we are today. There isn't very much significant that's different now in 2022 than there was in what, 1957, I think, when the transistor came out, roughly. The concepts are all the same. No moving parts. It's durable. It can change state very, very quickly. Obviously, we are literally millions of times faster, much more durable, and smaller. You don't even want to think about it. Like, it's unreal how much smaller they are now. But that's all we have to, it's all we have. That's all there is. So that's enough, I think, for the evolution of what do we use to indicate ones and zeros. Anybody have any questions about that stuff? Okay, good. Let's go ahead and move back. And by the way, I do want to look here just to show you all. Now we've gone over the simple explanation. If you try to look at Wikipedia on this without the simple explanation, it's a nightmare. So semiconductor, I think we can roll over this, relies on the electronic properties of a semiconductor material. They've replaced vacuum tubes in most applications. They conduct electric current in solid state rather than free electrons. We're not even going to get free electrons. So we can switch electrical signals, basic building blocks of modern electronics. So let's see if we have history. First working transistor. Look how big that is. It's almost 2-3 inches tall. Now, where are we at now? They are nanometers in size. Nano means 10 to the minus 9th, I think.
1 billions.
Yeah, 9 zeros. So that's millions, 1 millionth. Yeah. Oh, billionth. Yeah, nine, sorry, billion. Because 6 zeros is million. I'm a genius. Once you go past that. All right, so 1 billionth part, super small. Okay. It's unreal, but it's the same concept. Nothing about it has changed. It's still that electricity comes in one side and can go out the other side if you have a gate signal that comes in. That's it. Any questions about this stuff? Yeah, there's Bell Labs, American Telephone and Telegraph. They were the big boys. And they did some amazing stuff. All right, good. That's enough. I didn't want to cover any more of that. We don't need to go a super deep dive on it. I just want you to understand that modern transistors operate on the same basic principles as the vacuum tubes, and they're very small and they can operate really, really fast. Okay, good. So let's get rid of that. And let's look at our next material. All right. And do I have, I want to see if I have no chats. Okay, good. That's fine. All right. I want to make sure chat's set up well. I've got 2 viewers. If you're viewing, can you throw something to the chat to make sure that it's working? Okay, let's talk about a concept called networks. Can you tell me what network means?
Just wait for 2 devices to communicate with each other.
Good. Yeah, that's really all it is. The moment we decided to connect computers together, the concept of networks came together. So here's my question. Why would you ever want to connect 2 computers together?
Would it be to like share data?
Good. Good. Now, what's the basic purpose of a computer? From day one, I've harped on this basic purpose of a computer. What is it?
Data processing.
Yeah, to take data in, to process the data,
and output.
right, and to pass it on. So, if that's true, then why do we need another computer involved? Let's say we have a big old pool of data here, and we have one poor little computer that can do the actual processing. And then it's going to send it on. You're going to reach a point where the size of the data is so large that this one computer can't do the job. Or rather, it would take an impractical length of time. What do you do? How do you handle that?
Would you just use more computers then so that more different ways to process it?
Exactly. Part of the reason I'm going through this is because as you move into the industry, there's a lot of complexity. I'm not going to call it apparent complexity. It's genuine complexity. But every single element of it that appears to be complex on the surface and is in fact complex, every part of it breaks down along fundamental lines. And here's an example. You are absolutely right. Why don't we take this stuff right here and let's give ourselves 5 computers. And then we split up the data. A chunk of it goes to the first computer. A chunk of it goes to the second computer. A chunk of it goes to the third. A chunk of it goes to the fourth. And a chunk of it goes to the fifth. And they each do some processing. They each have part of the work. And then they take their results, they combine them, and therefore all work is done. Now, here's my question. Does every single computer do 1/5 of the work in this scenario? It looks like it, doesn't it? We divide it equally. 20% here, 20% there, 20% there, 20% there, and 20% there. That means we've got 100% of the data, pardon me, of the data. And here's the question I have for you. Think about this. Are these five computers going to perform this work in 1/5 the time? What's your first instinct?
No,
Why?
I don't know. I honestly don't know.
Well, that was completely fair because it's clear I'm asking a trick question. So here's my question. Because it sure looks like, yeah, Eric, we have 5 computers, assuming that everything else is constant and there are 5 identical computers. Why wouldn't they get the job done in 1/5 the time? Well, I just magically drew some lines and said, let's give 20% of the data to this one. And let's, well, who's doing that? Who's dividing this data up and farming it out to each of the 5 computers and then grabbing it all and combining it into a complete processed package of data? You
Another
only have
computer?
go ahead. What?
It's another computer.
Exactly. You only have 2 possibilities: a magical 6th computer, number 6, or you take one of these computers and part of its resources are assigned to being a manager, controlling this process. That one computer might have a special program on it that goes through and does the, let's switch it over to yellow, divides the data into chunks of 20%, assigns it some to itself, and then some to all these other computers. And then once all the work is done, collects all the processed data and combines it all. We would have one tiny little part of the processing power of that computer that manages the whole process. So therefore, this one doesn't get to do 20% of the work, or it doesn't operate. This whole thing isn't done 5 times as fast. It might be 5.0001% times faster. Oh, wait, sorry, I did that backwards. I apologize. We might get 4.9998 times as fast. And that's the only reason why. As soon as you have this network of computers and you're divvying up the work, someone's got to run that process. You can either take some resources from an existing computer that's in the very system that's going to do the work, or you have to bring online a whole nother computer. But either way, you don't get 100% of the processing power of all the computers that you're dividing the work on, among. Any questions about that concept?
I have a question. Would it be faster then to just use a 6th computer than to take some of the resources from one of the existing computers?
It would, but then let's say you have computer number 6, and let's say it has this much capability. We're only using a tiny bit of its effective ability to manage this whole process. And now we've wasted CPU resources and memory resources. So you have to make a decision. So yes, it would end up being faster, but now you spent money for a computer you're not using.
Okay, yeah, that makes sense.
Yeah. By the way, on this screen right now are many reasons why the cloud is a big deal. Let's look at one. Alexandra brought up an incredible point. Well, wait a minute. Why don't we shift this little, tiny bit of computer number one, or we'll call it computer 1, 2, 3, 4, and 5. We've been stealing a little bit of computer number 5's processing power and memory to manage the whole process. Why don't we offload all that and put it on computer number 6? And she's absolutely right. But as she and I were just discussing, now you have a very underutilized computer. Well, what if we said to someone else, hey, would you like to rent the other part of this computer that I'm not using? I'll let you have some of the clock cycles. Click, 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 2-3 billion times a second that clock is going. I only need about 20% of those clock cycles, 20% of the available processing power. And I only need about 20% of the available RAM. You can have the rest. If you install a program on here, just as long as we can manage this process where I still get my work done, you can have the rest. That's the cloud. Right there. You are renting part of the capability of computers that other people own. Any questions about that? Okay, good. Now, let's step back a second. I asked the question, like, why would you want to connect computers to each other? And the first answer was totally correct, which was to send data from one computer to the next. But that function of sending data from one computer to the next doesn't get any work done. It doesn't result in the purpose of a computer being accomplished. What's the purpose of the computer? To take in data, to process that data, and to send it on. That's the purpose. So you'll find that when you're sending information back and forth between computers, the reason that you're sending the information is so that you can actually do the work of the computer. The sending of the information is not work. It's totally valid. I'm not trying to point this out like the answer is wrong. It was a totally right answer. I'm not trying to point this out like it's a bad thing to send information from one computer to the next. Not at all. I need you to think as engineers with the fact that when you are sending information from one computer to another, that is not work. You're only doing so to ensure that the overall work that can be done. In other words, we call it the computational task. Now that's a fancy phrase for the work that we need to do. That's our computational task. The situation we had before was that our one tiny little computer, let's say we had this one right here, couldn't get the job done because the data was too big. The job is the computational task. We divided the computational task into pieces. We divided the work into pieces. If we have these 5 computers and they're going to manage this job, then information is going to need to travel back and forth between them. Hey, are you done yet? No, I'm not done. Okay, I'm done. All right, let's wait until we're all done, and then we'll all assemble our data into a central file. Okay, there's communication back and forth. That communication is not work. It is communication needed to manage the actual work that gets done. And you'll see that pattern over and over and over and over again as you build programs. And so I just want you to think with what it is. Communication between computers is not work. It facilitates work. Any questions about that? Okay, good. So let's talk about this whole idea of networks. There's a bunch of structures to networks. We're only going to cover a couple. You might have, let's switch to black here. network. They call it architecture. And by the way, I'm about to give you some gross simplifications. People who are network architects will want to hit me, but that's their area of specialty and they need to know it really well. We don't really need to know it very well right now at our stage of our career. There's a few things we would want to work with. One of them is what's called a ring architecture. Here's a computer, another one, another one, another one, and then I'll switch to blue. Information can travel back and forth in this manner. So let's say we numbered these. And now let's say we do have some data that is on computer number 1, and we need to get it to computer number 2. What do we do? How far does it have to travel?
Just the one
Through
computer.
all of the nodes.
It actually, we just go here, typically. That makes sense. Now, let's say we need to get something to number 5. Same thing, right? Has to travel one computer. Probably shouldn't take very long. Well, let's get really mean. What if we need to get over here to number 4? How would it get there? You have 2 paths, right? This isn't a trick question. What are the ways you can get there?
Through 2 and 3.
Yep, it could go this way. And what's the other route?
Through 5.
Through 5. Okay, good. So here's my question is, can you think of a condition or a situation where you wouldn't want to just send it through 5? Why go through 2 computers when you can go through 1? Can anybody think of a situation where that might happen? Or make sense?
The capacity.
Good.
If
When you
mo-
say, go ahead. I'll let you talk as well. Go ahead, Jason.
No,
Your
I'm sorry.
capacity.
Yeah, that's what I was gonna say. Go ahead. I'm sorry.
Excellent. Good. So let's assume that all the computers are equal in terms of CPU, like speed, and the available RAM they have, and their hard drives. Let's say they're all perfectly equal. So when you say capacity, define exactly what you mean by capacity. Do we mean this combination? Because they're all equal capacity. Jonas, are you the one that said capacity?
It's
I
the
didn't hear
process.
Or was that Sudesh? Sudesh, go and explain what you mean.
It's the processing capacity,
Good.
data
So
processing.
when you say capacity, what do you mean exactly by capacity?
How much data it can have at one time.
Okay. So then tell me again why you would ever want to go through 2 to 3. Why would you want to go through 2 computers? If they're all equal capacity, all equal ability, why would you ever want to go through 2 of them instead of through 1 of them? You're on the right track. You're exactly right. And you're probably saying the right thing. I just want to be extremely precise here.
at that moment, if 2 and 3 is, if 5 is using more data, it will
Yeah.
take 2 and 3.
That's exactly what it is. It isn't like capacity. You need to be very precise. Another way you would want to look at this is load. And this really means, let's say you have the available capacity from 0 to 100. How much of that is being used on any given machine at that exact moment? And you're totally right. If 5 is at like 95% of its CPU and its RAM are being used, and you want to send data through it, it's actually going to end up being slower, potentially, than going through 2 and 3 if they are at about like 10% of their load. So it isn't the capacity. Capacity indicates the upper bound, the potential. I know you were answering the question correctly, Sudesh. I know you understood it really well. I just want to make sure we use the right terminology here, the right concept. Of the available capacity, how much are we using? That's load. And we're going to come back to this concept over and over and over again as we build software. So again, there's a whole lot of other factors involved in how you run networks and what a ring network will look like and everything. I don't care. We don't need to know them right now as engineers. If you're dealing with situations later in your career where this is a real big factor, fine. You can do the research then and get really nerdy about it and dive deep. I just want you to think with the central concepts, and you guys are doing a great job at this. At any moment in time, any one of these computers, these places where computational work can get done, we just need to pay attention to how much is currently being done when we decide whether or not we're going to ask it to do more. That's all. That makes sense. Any questions about that? All right, let's move on to arguably the most common architecture, which is a client server architecture. This is a network architecture. Remember, we're looking at types of network architecture. How does a client server architecture work?
Basically, the
ideas?
clients get the information from the server.
Okay, good, good. Now let's break that down. This is good. So we have a computer, and it is a server, and we have multiple client computers. Good. Didn't mean to do that. There's client computers. Now, the first thing that Jason said, and he's spot on, is there's information that's on the server that the client needs. Now, in general, why would the client need information from the server in general?
Server has a lot more processing power, and there's usually a lot of clients that need information from that server.
This is all very true, but what I mean, like even in the more abstract, why would one computer, in this case the client, need some information from another computer? Just in general.
So it knows what to do.
Bingo. This information can be instructions. This tells it how to do its work. Good, thank you. It can be data. This is what to work with. So that's what can go back and forth. That's all. Again, this is rock dead stupid simple. I'm not trying to be like odd here or like complex, because it isn't complex. The client needs information that either tells it what to do or gives it the thing it'll do stuff with. That's all. So there are two reasons for this client-server relationship. There's two things. What can a server do to help? This is literally the way to think of it. Because a server is there to help others. They are a servant to help. So the one way they can help a client is, one, they can give data to clients. We've already covered what that might be. It might be instructions on what to do, or it might be the data to be worked with, but they can give data to the clients. What's the other thing that a server can do to help? And this falls back to the primary purpose of computers.
Receive data from the clients.
Good. Why would a client want to give data to a server?
To share with other clients.
True. If you want to have that kind of a stop, you could have data go down to the client and then out to another, down to the server and then out to another client. You might want to do that. Or you just send it directly to them. Here's where I'm getting at with this. When you are looking at networks, and when you're looking at computer programs and how they're designed, here's the biggest question you need to answer. Put it in big giant letters. Who is going to do the work? So much of computer program design and network design and everything we do as technologists is simply trying to answer this question. That's all we're doing. So let's look at this situation. The reason that a client might want to send information to a server is the exact same reason a server would want to send information to a client. It's either instructions on what to do, or it's data to do the work with. So this tells you the answer to the second question. If these questions are, what can a server do to help? One, it can give data to clients. Two, it can do work for the clients. Now, there's a lot of complex stuff involved in making networks work. I am so in awe of people that are networking professionals. I'm describing this in very high level terms, and I sound so certain about what I'm talking about. And I am certain because I'm just dealing with the fundamentals of computers and why we made them in the first place. But they're the ones that have to make all this work. And it's very incredible work. As an engineer, unless you are going to deal directly with how the network itself operates, you just get to take advantage of all this expertise that they have. And the part that you need to know now at this stage of your career is just these high-level things. The purpose of the computer is to take information in, process it in some fashion, and then send it on. And most of the time, we just spend our work time answering that question. This client server system was just one way to answer the question. The question is, who's going to do the work? The client can do some work, in which case it might need information from the server, like, give me the raw data that I'm going to do the work on, and I'll take it from here, thanks. Or it might need information from the server, like, listen, I got a bunch of raw data, but you have like a program I'm supposed to run, like a specific series of actions. Can you give that to me, please? That's all I need. I'll take it from here. That's the client saying to the server, give me information, please. I'll do the work. Thank you very much. That's number one. Number two is the client saying, listen, I just collected a bunch of data. I don't really have the ability to handle it right now. Thanks very much. So I'm just going to give you the data and some instructions on what to do with it. You are Mr. Big, beefy, awesome computer. You can get this done a lot faster than I can. You take care of it for me. And when you're done, give me the results. That's actually all there is to it. That's all there is to client server. The server can either give information to the clients so the clients can go about doing their job, or the server can do the work for the clients. And I'll tell you something, we go back and forth between where's the best way to do it. This question I had of who's going to do the work, there's no set agreement on that. We're going to see that move on to our next stage, which is what is the internet and what is the World Wide Web? But that's networks. There's only one other network that I really want to get into, but I want to make sure, do you have any questions on a ring architecture? Any questions on a client server?
Is the ring architecture still in operation?
I haven't seen one in a long time. I don't even know an instance where you'd want it. But you encounter that term. I wanted you to understand what it was. And what I really wanted you to understand was this load issue. Being forced to make a decision about how your computer is going to cooperate and work with each other based on how much load is there at various points in the system. That was why I wanted to go into that. But no, I don't see it very often at all. It was a good question. Any questions on client server? Okay, good. There's only one other, and I'm not going to spend a bunch of time on it, but I want you'll see it, and we'll come back to it maybe later on in our work. And that is peer-to-peer network. Now I want to point something out. We had this really interesting ring that we made. And I want to call your attention to something. The very reason we had the discussion about how long or what decision to make if we wanted to send data through this. The very reason we had that discussion is because in our made up little situation, computer one was not permitted to talk directly to computer four. That's how a ring works. A peer-to-peer operates a little differently. Number 6 can talk to 5 or 4 or 3 or 2 or 1. Number 5 can talk to 6 or 1 or 2 or 3 or 4. Number 1 can talk to number 2, 3, 4, 5, and so on and so forth. Does anyone know what the word peer means?
Like you're equal.
Yep. You're equal in rank, importance, etc. Peer-to-peer is different than ring. Now, ring, these are all peers. They're all on the same level of importance. Client server, absolutely not peers. The server is considered typically higher than or elevated at or importance or altitude than the clients. So they're not peers. Now, the difference between this ring right here, where all of the computers are basically equal, and here is that you are allowed to communicate from any peer to any peer. Now, does anybody know some popular places that this particular network structure is used?
BitTorrent.
BitTorrent. What is BitTorrent? Come on, you know what BitTorrent is. You said it.
Oh, I didn't know you were actually wanting the
Yeah.
answer.
Yeah, what is BitTorrent?
Just a bunch of computers connected to each other sharing files. I mean, basically.
File sharing. Tell the truth. What kind of files do they share?
Well, Linux distributions
This is good. Okay. Operating systems.
and movies and media and stuff like that.
Oh, movies, songs, video games. And I'm sure that all this, they pay the manufacturers and creators of the movies and songs and games, don't they?
Well, I do.
I know, because you're awesome. Now, most or many of the people that use this kind of a system called BitTorrent do not, in fact, pay for the movies or the songs or the games or whatever they're getting. What they do is this. Let's start to use green here for a moment because we meant data. Let's say that the data is a movie. Now, let's say that we have 3 people, because these computers are owned by people, and every single one of them owns this movie, and it's on their computer. Now, let's say that the person who owns computer number 2 wants to have that entire movie. He can use a program like BitTorrent to send communication out throughout the network. Here he is, and he communicates with literally every single computer in the network. And he says, hey, I want this movie. Any of you have that? And he gets positive answers back from computer number 6, computer number 4, and computer number 1. He says, okay, good. Hey, BitTorrent, go get that whole file for me. And so BitTorrent gets part of it from computer number 6, part of it from computer number 4, and part of it from computer number 1. And it manages that whole process. It's a torrent or a flood. That's what a torrent is. It's a flood of data. It's a flood of bits, hence the name BitTorrent. So BitTorrent manages peer-to-peer communication. And the reason that people can get away with not paying the money is because the other way they would get the movie is that there's a server, say an Amazon server, just to pick the biggest retailer on the planet, and you are a client, and on the Amazon server is the file you want. I meant for that to be green. I apologize. Hold on. Here's the movie you want, and it's stored on Amazon's computers. Because this is a client-server relationship, if you want that data so that it can play in your video player on your computer, then you have to issue a request, you have to pay money, and then you get it. Because the client-server architecture allows central control. Peer-to-peer has absolutely no control possible in it. Any questions about peer-to-peer? Now, can anybody think of like a like an ethical, smart reason why to organize things this way?
Protect privacy.
Good. I love that. You're absolutely right. If communication needs to go back and forth to people and they don't want to have it go through a server where you're going to get authenticated, they know who you are, that's absolutely a good reason for it, Sudesh. The biggest reason comes back to what we talked about before. We said, give us this example where there's a massive collection of data, and we really want to divide that amongst a lot of computers. Well, here's one of the most popular or well-known uses for peer-to-peer. It's called SETI. Can anyone tell me what SETI stands for? Search for extraterrestrial intelligence. We have all these radios all over the earth, and they're all pointing out towards space. And they were collecting an incredible amount of data. We're talking thousands of radios, massive amounts of data collected. And they were trying to analyze it for looking for signals that look like they might be an indication of extraterrestrial intelligence. Now, SETI didn't have a lot of funding. You can read all about this on Wikipedia. It's pretty cool. They couldn't afford to buy a bunch of computers. So what they did is they put out an open call and said, hey, listen, if you're willing to help process all of this data, we have a little teeny peer-to-peer program that you can install on your computer that'll let you be part of our little network. Well, the little network eventually had millions of computers all around the planet that all had the same little piece of software, and they all cooperated every day to pull down data and process it and then send it back with their results. That is a phenomenal example of peer-to-peer. Each one of them could do a little teeny sliver of the work. No one computer was trying to do all of the work because there's no way. So they divided the computational task. Good, that's enough for now. Enough history lesson. All right, here's what I want to do is it's 9:20 right now. I want us to take a break, okay? So we talked about doing breaks and we're going to do it. And bio break would be good. And then when we wrap up, when we come back, we're going to end off on something that really you are going to return to the fundamentals of what we're about to cover with the difference between the internet and the World Wide Web over and over and over again in your career as an engineer. What we're going to cover is some of the most important fundamental data that you're ever going to have as a developer. I'm super excited about it. All right, let me go ahead and switch over to a timer. I'm going to pull up, I think, an egg timer. It's called egg timer. I found this the other day. Yeah, here it is. Egg.timer. Let's do 10 minutes. All right, good. Okay, I'll see you in 10 minutes. Hello, all.
Hey,
Cool. Okay, welcome back. All right, so here's what we're going to cover. We're going to cover the difference between the World Wide Web and the internet. Now, we're going to add more and more detail to how this works as we move through the curriculum, but these fundamentals will always be true. And we will fall back on these fundamentals often, okay? And again, it's going to be quite a simple picture I'm going to paint right now. We're going to add more and more nuance to it in times to come. So, the internet. It is only two things. One, it is a large network of computers. Large could be underlined about 1 million times. Two, it is protocols for exchanging information or data between them. That's all the internet is. Notice that what the internet is not is web pages, websites. In fact, software of any sort. The internet is completely and only physical or conceptual. This is physical elements. These protocols are just concepts. A protocol, can anybody tell me what a protocol is?
Is it like the rules for instructions or something like that?
Good, absolutely. We can call them rules. What they really are is just agreements. More precisely, they are broadly held agreements. In this case, they're literally published. Protocols get published. The highest level protocol for the internet is called, you ready for this? IP, for Internet Protocol. Right underneath that is something called TCP. Anybody know what that stands for?
transmission control protocol. I don't know if that's right.
It's Transfer Control Protocol.
There you go.
And here's the thing. Most of the time, you don't even need to know really what these are and how they work. There's points in your career where you'll get closer to these and you really need to dive deep into them. But honestly, you seem to know that they are agreements about exchanging information between computers. What computers? Well, the ones that are on this big giant network called the internet. By the way, this tells you you can have a network of computers that's not connected to this network. You could literally have an office building. Here's an office building with all these levels in it. And in it are a bunch of computers, and they are only connected to each other and nowhere else. They don't connect outside the building to all the computers that are the internet. This would be a private network. It's not connected to the internet. Let's take an eraser and move that arrow. But we're not talking about those right now. We're talking about the internet. Okay, so there's the internet. It's both a network of computers and protocols for exchanging data in between them. Now, there are a lot of different kinds of data. We're not going to explore all of them right now. When it says data, just know that there's lots of types. For example, email is a type of data, and there's a protocol for it. It's the simple mail transfer protocol. There's another type of data, which is just large files. Doesn't matter what type they are, a big file. That's the file transfer protocol. And then what's the web? It's only one thing. It's a collection of linked electronic documents. That's all the web is. Now let's talk about that a little bit. Imagine, if you will, that you were in a library. And in this library, they had a book. This book was on dinosaurs. Now, let's say that this was, because I'm a Harry Potter fan, a magic book and a magic library. And there was one particular word in a paragraph that if you actually put your finger on that word, another different book entirely that's in a different location of the library would fly over and open up right next to you, and you could read it. Because there was a link established between this word and this distant book. That would be pretty cool. And also, it's not possible. But that's the concept. It's actually all there is to it. What we have instead is this. We have computers. They have files on them. Here's a bunch of files on a computer. Here's files on another computer. Now, some of these files are what we call electronic, electronic documents. It sounds all fancy. It's just text files. They're just text files. There's nothing magic. But they're special. Some of these documents, and there's documents over here as well, some of these documents have defined in them connections to other documents or documents on the same computer. And there's connections from there to other documents. Lots and lots of connections. The documents are the web. It's a collection of linked electronic documents. Now we're going to get into a lot of specifics about how you form those links and what kind of computers you can store these things on. But that's actually all the web is. Any questions so far? Okay, let's add a little bit of nuance to it, and then we're probably going to call it a night. Here's the nuance. The web was designed to use a specific network architecture. If we have this big giant collection of documents, where are we going to put them? Well, we're going to put them on computers. What structure are we going to have to the network? What architecture do you guys think this network has? We covered 3 architectures tonight. We covered ring, client server, and peer-to-peer. What architecture do you think we use for the web?
The client server one.
Absolutely. Here's a server. Here's another computer. There's a client. Now, let's fall back to the fundamentals we were talking about a little while ago. There's only two things a server provides. One, it provides data. And two, it provides work. It's a gross simplification, but it's true. So in the web, what it can provide is data. More precisely, what's on the web, on this server is files. They are pages called web page files. But this is what's super important. They're just text files. There's absolutely nothing special about them at all. They're just text files. Over here on the client, it wants that data. Why does it want these text files? Well, because I lied. Because these files aren't just text. The text in them is structured. Yes, I did tell the truth. It's just text, but it is precisely structured text. Why? Because it is data, and data goes into computers, but more precisely, computer programs take in data. And the data that we're talking about in these files that's in text form needs to be structured such that the program that receives it can scan through it and find what it wants. What you're looking at here, without a bunch of fancy terminology, is the anatomy of the web and the work that you will do as full stack developers. We haven't gotten into specifics of terminology and how do you structure this text and what are these programs and what are they used for. I just want to reinforce the simplicity of the fact that the web is just a collection of linked electronic documents. You have to store those documents somewhere. When we store them, we call the computer we store them on a web server. And if anybody needs those files for whatever purpose, those are web clients. Now, again, there's lots of other terminology we're going to learn. We're going to learn all about how to structure these text documents. We're going to learn about this web server and things it can do besides just serving up these files. It can do lots of other stuff. Remember, it can do work. We're going to learn about how these files are made. Can they be made on the fly? Or do they all have to be prepared ahead of time? We're going to get into all of that. But this is the fundamental. The internet is just a giant network of computers and some protocols for exchanging data. Some, but not all, some of those computers in that network happen to be involved in this business right here, working with a giant collection of linked electronic documents stored on computers all around the world. Those computers happen to be some of the computers that make up the internet, but they're separate things entirely. Any questions so far? All right, now we've already added some nuance to the difference between the internet and the web. And right now, many of you already knew all this stuff. Some of you may have learned some new stuff, learned something tonight. Okay. I can tell you that you know more than a lot of people on the planet about what the web is and what the internet are, even right now. What I want to caution you against is now telling people they're wrong when they say, I found it on the internet, for example. I bought it on the internet. Not true. You bought it from a web page. You bought that off the web. Who cares? Not worth fighting about at all. Just let people be right. I don't think anybody in this class would do that to anybody else, but I just want to caution you against it. You're going to start to become possessed of even more extremely valuable, specialized knowledge. You already have a bunch, but as we go through this training, you're going to get a lot of very specialized, incredibly valuable knowledge. Don't ever let it go to your head. Continue to be the awesome, compassionate, cool people you are. All right. That's the material I have for right now. There's a lot more we're going to dive into on the internet and the web and everything tomorrow night. But anybody have any questions so far? Okay, cool. All right. We're not at the stage where I have any homework I want to give out. What I'm going to do is do tonight and tomorrow night, and then I'll give you homework for the week. I'm going to give you back about 15 minutes of your night. Anybody have anything they want to cover before we end this off for the night? Okay, cool. Excellent. And again, we'll pick it up tomorrow and get some more terminology involved, a little more precision about how all this works. It's a lot of fun. But now what we're learning over these two sessions, you will return to over and over and over again as a web developer and as a full stack developer. Okay, cool. Thank you all for doing this. Appreciate it. Glad to have you. It's good to see you all again. I'm sorry it was a week. That was just a really bizarre week. I'm glad we survived it. And I appreciate you all your checking in as the week went by. Other than that, I will see you all tomorrow night, same time.
Good night.
Cool.
Thank you.
Well,
Thank
good
Sounds
morning
good.
to you.
Thank you.
Thank you.
Yep.
Bye.
Bye. Al.
Thanks.
Bye, everyone.